So a very good day once again, and welcome to class. Can you all hear me?
Yes,
Yes,
sir.
sir.
Oh,
Yes.
okay.
Yes, sir.
So well, I think we'll try to run through a few details today, and if we've got some time, we'll try to do a little MATLAB coding. I know last time we had a little introduction, in terms of relative to the use of MATLAB. So that's one aspect where you just have to write your end file. What if we want to, conduct a little programming where we have to have some files calling some other files. So we'll call those such files function files, okay? So if we've got some time, we may run through that, but I'll just show you a typical example, which we'll talk about much later. Let's see if I can share it, or can I share my MATLAB? Okay, let's see if I can do that. Okay, this is my MATLAB. Okay, so this is what you guys played with last time, and okay, now this is more like a function file. Okay, and this is the file calling the function file. I just wanted to show a little, just to describe this while some other guys are coming into class, but you don't worry. We are going to try as much as we can to get our hands dirty as we progress in the program, doing, some kind of stuff using MATLAB. Now, in this case, we just ran through an example, described all we wanted to do in a single script file, and boom, we got our plot. Perfect. So we played with this last time. So I have what I want to do. I just have to run my code, and then I get my result. But the more robust what we have to do is, or become, then the more we have to devise a means to probably, let's say, to organize our files. So I don't want to compress all my codes in one file, having a very long list of whatsoever. Probably I want to have multiple files talking to each other, just to make things a little nicer or cleaner. So in that case, you want to have function files. Now, when you use the word function, then the function name will be the name of the file when saving the file by default, okay? So you see that here, function is saved with this, classify underscore signal. So I just want to classify some signals. I want to know if it's a continuous time signal or a discrete time signal. It's just a simple example, okay? So in this function file, I just define this, and I have X, my signal, and then the type. So this is an if-else statement. So if the type is continuous, then tell us that the signal type is continuous time signal. As if the type is discrete, then it's just tell us the signal is discrete. Else, if none of those options, then we don't know what it is. Then we end the program. Now, that's that. But I have to now create another file that we call the signal type. Okay? So we are more like saying X is equal to Y, right? So what we are not trying to say is that, fine, I have another file which I could call anything. It's not going to tell me the signal type 1. So I wanted to classify it. If it's this, then it's continuous. Then if it's this, then it is discrete. Then display that. So I'm calling this particular file type. Now, you have nothing to worry about. We are going to play with this as we progress. We'll do some kind of, we'll definitely design some M files that will play with your function, the function files, and also the regular script files that we just have to do everything on the page and then plot, okay? So that if I should plot this, then I run, then it's going to tell me, well, signal is this or signal is that, okay? This is just a simple basic thing, but we'll do some things, we'll do more complicated or sophisticated activities. Okay, this is just in passing, so you know what we'll come back to. Okay, so now I'll just share a slide now. So can you see our slide?
Yes, sir.
Yes, sir. Yes,
So,
sir.
so you can see signal classification and manipulation, right?
Yes. Yes,
Can,
sir.
now, can you see the blank page?
Yes, sir. Yes.
Okay, perfect.
Yes.
So it means everything is just as fine. Now, before I move on, I would love to, entertain a few questions. Probably in your study and going by what we tried to address in our last class. Is there anything you want us to clarify at this point before we move on to signal classification and manipulation? Anything?
Yes, sir.
Okay,
Good
please.
afternoon, sir.
Good afternoon.
Sir, while reading the fundamentals of electrical engineering, I noticed terminology is very, very similar to that of the signals and systems. So I wanted to know, like, in a summarized form, like, what's the relationship between this course and the electrical fundamentals of electrical engineering course?
Okay. Very interesting question. So this also should address the relationship between signals and systems and every other course you get to take in your program, okay? Be it in biomedical engineering, be it in electrical computer engineering or systems engineering. Now, the idea about the fundamentals of electrical engineering is that it equips you with the necessary tool to solve problems. So it doesn't give you an exact solution or a particular approach to solving a problem. So it exposes you to diverse techniques or approaches or methods you could use to solve the same problem. Okay? So you could get the same answer using different methods. That's the idea. So what you're trying to develop in your fundamentals of electrical engineering is the ability to solve problems. Only that it is tailored towards addressing electrical circuits. Okay? But when we talk about the electrical circuit itself, it is a system. Okay? It is a system, largely because it is a body of signals and systems. Let's put it that way. Largely because whatsoever you want to drive, you have to have an input, process it, and then an output. Okay? So I think that is the direct relationship. But your signals and systems, your electrical fundamentals are all, they consist or contain the body of knowledge to build your foundation in the engineering study. Is that fine?
Yes, sir.
Okay. And one more thing, if you feel the videos are helpful, the lecture notes are helpful, then you could share among your friends that may be outside the faculty. So tell them they could subscribe, they could share, and don't fail to like the videos if they're helpful, and then you could also leave your comments, okay? Is that okay?
Yes, sir.
Okay.
Yes, sir.
Okay, so then we just move on then. So last time we played around, well, we'll be talking a bit today. I wish we were in a physical class, probably would have done a little think per share, where we're able to spread ourselves into groups and then give ourselves some tasks to address a few problems. But nonetheless, in this class, I may end up, throwing an idea to us so we could just reflect and then probably put our contributions, okay? Yeah. since we do not have breakout rooms right now. So we were able to detail in our last class that signals, forms the body of abstraction of some measurable quantities, okay? Where we are able to relate some dependent and independent variables. And then we said, well, one function must be changing with respect to the other to have a signal. So if we have a constant parameter, then in the process where we are supposed to be having some level of variation, we say, well, we do not have a signal. We were able to also mention last time, we were also able to mention last time that we have single value or single variable and multiple variable signals. That we were also able to mention that signals are classified to be either continuous or discrete time signals. Same with systems, but the abstraction in terms of system takes an input, it operates on it, then it gives us an output. So this time we want to look into something more interesting, okay? Yeah. So in other words, if we also have a system, it means it should be capable of taking the input and giving us output. So whatsoever we have here makes a system. So it means there's an interface here, there's an interface here, then there's some circuitry, maybe your electrical circuit, the mechanical circuit, it could be anything, that now have to operate on all of these excitation to give us the required response. And then we now also mention, we then went on to mention that the closest approximation to a system we would love to design is the linear time invariant system. Well, this may not be achievable in practice, but it gives us sufficient approximation to design systems, likely because one or two tolerances will definitely result in some form of deviation from the ideal, okay? Yeah, so, and you see that, well, your rotor is supposed to rotate at a certain speed in terms of the revolutions per minute, but now if we should consider mechanical errors, some, basic calibration issues, then the flux itself, the magnetic and whatsoever interaction within that system, then we now realize that, fine, we are getting close to that, but we are actually not getting the theoretical value, okay? So don't forget, this is an approximation, okay? An approximation, okay? So it's an idealized system. It's idealized. It's not a practical system, okay? Good. Now, also in our last class, someone took us to the deterministic signal, and where we had to argue, if the DC is not a deterministic signal. But where we said, well, the DC is not a deterministic signal, but a unit step function is a deterministic signal, okay? Now, it may look like the DC, but actually it is varying, okay? It's just moving from some zero value to some positive value. But the DC is the same value either at the negative time axis or the positive time axis, okay? But for our unit step function, we see that it takes on value. So at the negative time axis is 0, but at the positive time axis, it is positive. So there's some level of discontinuity at the origin. And as such, it maintains a certain value, at different time intervals. So this unit step function is deterministic signal. It's a deterministic signal. So we can classify this as a signal. It's a signal, while this is not a signal. Okay, just to clear all that. So we already know that in terms of classifying signals, signals could be classified or categorized into two broad groups, which we already mentioned. The continuous time. We have the continuous time signals, and then the discrete time signals. So here we could say this is continuous time, then this is DTS. But at times it could be confusing. When I'm talking about system, I just say continuous time systems, discrete time systems, the DTS. But, well, we should know the context, okay? So CTS, DTS, sometimes, you just want to be sure if we're talking about the system or the signal. But regardless of this grouping, we also have that signals could either be analog, okay, and being analog, we just know this is continuous, okay, and we actually interact in the analog domain. So this is a continuous time signal, say, S of t that can take on any value in the continuous time interval. So as I'm moving from the negative time interval to the positive time interval, we can actually assign a specific value to this signal. So we say this is analog. Now, the digital signal, on the other hand, so they say S of t, then the digital signal, S of n, is a discrete time signal, okay? So we say digital. This is a discrete time signal that can equally take on finite number of distinct values, okay? So there we could say, well, we are moving from some high state to some low state, all the way, we say, well, this is a digital signal, okay? So we could say S of t. So where this is the time interval. So let's designate that properly. This is the time interval. So our time space here is n. Then we say x of n. We already specified that our discrete signal, we designate our discrete signal using the square brackets, while the normal brackets, we use it for our continuous time, okay? Then in your elementary mathematics, you played with complex numbers, right? Complex numbers. You say x plus j y. Let's put it that way, it's equal to z or whatsoever you call it, okay? Where this is the real component and this is the imaginary component, right? Perfect. So the same thing, we can equally have a real signal whose value is a real number. We can also have a complex signal, okay? So the complex signal will definitely have a mixture of the real component and the imaginary component, okay? Where we know that j is the same as square root of -1. Then we already made mention of deterministic signal. In our last class, we made mention of the random signal, okay? Because the signal's value, cannot be determined distinctively at any given instant of time, okay? So it means the amplitude values cannot be easily estimated. So what we do at that point is to use some statistical techniques, okay, to evaluate the signals. And this also, now that we have complex signals, now that we have complex signals, then this brings us to even and odd signals. Okay, so Chidera, go ahead, please.
Okay, sir. Good afternoon, sir.
Good afternoon.
Just ask a question according to what you just said now. You talked about complex signal. I'm going to ask, since complex signal is talking about is the combination of complex of imaginary and real number. Can we also call that as a digital signal?
Okay, that's really interesting. Can we call it a digital signal? Why not? We can have the imaginary and the real component of a digital signal. We can also have the real and imaginary component of an analog signal. Because at what point do we digitize? Well, don't worry. We are going to come to that shortly. Okay? Because when we begin to talk about the complex conjugate signals and the like, so we're going to come to that. Because when we now have to do digital signal processing, we are moving from analog to digital. And then we want to do encoding. Now, we can't encode at the analog plane. Okay? So, and then we are now going to address such cases, you know, and I'll show more light, throw more light, you know, when I begin to talk about all of those complex conjugate signals and all of that. Is that okay?
Yes, sir. Thank you, sir.
Okay. So we'll move on. Okay, so even and odd signals. Now, when we talk about even and odd signals, you should understand that we are still talking in the broad domain, okay, of having to separate or better still analyze the complex signal. Because as we'll see shortly, the complex signal, say S of t, is the sum of the real and the imaginary signal, okay? And just like our friend asked, can complex signals be digital signals? So I just said, well, yes, because we have complex digital signals, right? The same way we have complex analog signals, okay? Because for us to make mention of these complex signals, then it means that it has an even and odd component of the signal, okay? Now, if you recall your complex numbers, your theorems, you recall that we can also place this as cos t plus j sine t, isn't it?
Sir, I can't see, sir. I can't see it.
The body is not visible?
Yes, sir.
Can you see S of t being the same as this?
No, sir.
I want not seeing it. Sir is on listen.
What's
No,
that?
sir.
You're writing on the word.
I'm writing on what?
You're writing on the word, on the word, signal classification. That we're writing.
Really?
So we can't see it.
And my board is clear. Okay, so I will just reshare, right? Can you see this now?
Yes, sir.
Yes.
Okay.
Yes, sir.
Okay, so we have to do something about that. So now, well, we just made mention of the even and odd signals, right? So I made mention of the complex signal. I said S of t. Said, okay, something just popped up. Let's take this down. Okay, fine. So we said S of t is the same as the real signal component plus the imaginary signal component, right? And coming from what our friend just, mentioned, well, we have complex signals. Can we say can we also say complex signals are digital signals, or do they only exist in the analog domain? Well, I said, well, we have digital complex signals, which will be the same as Sn of n plus J Sn of n. Okay, so just designate it that way. The bottom line is we have the real component and the imaginary component. Okay. And if you recall in your complex numbers, we can equally designate this as cos t plus j sine t, where t could be theta, right? Do you recall that? Hello? Okay.
Yes, sir.
Now,
Yes, sir.
if you recall,
Yes, sir.
now, if we say cos minus t will be the same as cos t, right? Y cos, no, that will be sine this time. Y sine minus t will be the same as minus sine t. Do you recall that also?
Yes, sir.
Sir. Yes, sir.
Yes, sir.
Which makes cos t an even signal and sine t an odd signal. Okay?
Yes, sir.
Yeah?
Yes, sir.
Okay. So now that brings us to what an even and odd signal is. Okay. Now we've been able to separate the components of a complex signal. So meaning a complex signal is the sum of the even signal and the odd signal. Okay. And now this is how signals exist in reality. So signals in reality, the signals we play with come as complex signals because they have the even and the odd component. When you begin to do your DSP, your digital signal processing, you'll come to that. Now, it means that the even signal, should we have S of t, or better still, let's not put it that way this time. Oh, no. I want to type this. So for even signal, it means that should I perform time reversal? Because you see that this negative is actually having impact on the time, right? So it means that I'm reversing the time. We're going to see how this works now. Now, if I should perform time reversal on an even signal, it should give me the same signal, S of t. So the idea is this. Let us try one signal right now. Let us perform time reversal. So let's assume I have this signal. Okay, this is S of t. So this is time t. This is +1. So this is 0. Now, if I should perform time reversal, so it means that this is S of t. So now I want to get S of minus t. So what I want to do this time, I want to multiply the time scale, only the time scale. Nothing is going to affect the amplitude, okay? So let's assume the amplitude in this case is 2, okay? So the amplitude remains. So we're only dealing with the time. So the amplitude still remains as 2, okay? But now, let's put the 2 above, yeah, 2. Now, if we should multiply 0 by -1, for instance, what are we going to get? It's still going to be 0. 0 times negative, 0 times positive is still 0, right? So if we multiply -1 by negative, that's going to give us what? No, this is positive rather, sorry. This is +1 because this is a positive time axis. We have negative time axis here. So now if we multiply 0, because we're performing time reversal in this case. So 0 times negative is still 0, right? Are you with me? I'd love to hear you. I would
Yes,
like. Now, if we multiply 1
sir.
by negative, that's going to give us what? -1, isn't it?
yes, sir.
So it means that the time reversal literally flips the signal about the y-axis. Okay? So it flips it. But you see that S of t and S of minus t are not equivalent. So this is not an even signal. Okay? Because should we perform time reversal on the signal, it should be the same for that signal to be even. So an example of an even signal should be some finite band limited signal. Let's put this up. Something like this. For instance, something like this. So let's say this is -1, this is +1, this is time, and this is S of t. Now, if I should perform time reversal, okay, so this is S of t. So I want to perform time reversal on this signal. So I'll start with my negative time axis. So if I multiply my negative time axis, so the negative times negative will become positive. So it flips to this side, it becomes positive, right? +1. And the amplitude remains. So 0 times negative, this remains my 0. So +1 times minus, the negative side, it becomes -1. So it flips to this side, -1. Now, is this signal the same as this? Yes. So while this signal is an even signal, this signal is not an even signal. So we're able to tell an even signal if the time reverse version is the same as the original signal. Is that clear? So it means that an even signal is symmetric or symmetrical about the signal axis, which is the y-axis in our case. So Habib, go ahead, please.
Good afternoon, sir.
A very good afternoon.
Yes, I wanted to ask something concerning your definition of even signal.
Mhm.
From the definition, it says that x of -t should be equal to x of t.
Mhm.
And in the first graph you drew what you said is not an even signal because there are two different graphs. But the description for even signal only says that x of -t should be x of t. And in both of the graphs you drew, the first one, both of them are equal to 2.
Okay, now, are they really equal? So we are going to figure out now. Now, in this, you're saying that these two are equal, right?
The value for x of t are equal for both.
The value, what is the value of S of t? Do you mean the amplitude value?
Yes, the amplitude value.
Okay, now the amplitude value is not what we're talking about. It's a symmetry. The symmetry of the signal is what we are particular about, okay? Because when we begin to do some signal analysis, we are going to get to that in operation or signal manipulation. We are still going to do that in this class, okay? If we've got some time. Now, you see that a signal, trying to wipe this, okay, you see that a signal,
Yes.
this is negative infinity, this is positive infinity. A signal at this point is not the same as a signal at this point. Okay? Because should we progress from the negative time axis to the positive time axis now, and should we progress from the positive to the negative time axis, you now see that while we are talking about time advance here, we are talking about time delay here. Now, when the signal is shifting to the back, it means that the output is occurring before we transmitted the input.
Okay.
Now, whereas when we are moving our signal to the right, it means that the signal output is occurring after the input was transmitted, which we experience in our communication devices. You cannot hear what I want to say before I say it. You only hear what I want to say after I must have said it, right?
Yes, sir.
Because there is a delay in the transmission process. But if there is an time advance in the transmission process, then it means you are able to read my mind. Now, technology is coming to that, okay, where I'm able to tell you what you are thinking about. Now, we already have some that have been able to gain mastery of the imaginary dimension. You call some of them prophets, right? They're able to tell you what you're thinking or what you did in the past or what will happen in the future. So they are able to, traverse that dimension, okay? So it's also a part of research where you could also investigate to say, well, how possible will it be? What technology can we model such that should I have that technology on, then I should be able to tell what someone else is thinking? Now, it's very possible. So we are getting to that, very close to that, So that's the idea. So that, fine, by way of observation, they all take on the same value except the symmetry. Now, while this is in the positive time axis, this is in the negative time axis. Okay? So the fact that this is in the negative time axis, it is different from this, although they have the same amplitude value. And the time scale, should we take the modulus of the time scale? If we take the modulus of this signal, then they will be the same. Because if we take the modulus of this negative, it becomes positive. But we are not taking the modulus of this. We are taking it as it is. So the symmetry, so when we flip about the y-axis, the signal is changing in this case. So it is not an even signal. But when we flip this signal about the y-axis, it's the same. It's more like we just rotated it. So this part came here and this part came here, but at the end of the day, we still have the same thing. So it means that all signals that are symmetrical about the y-axis, or in our case, S of t axis, are even signals. Is that clear, please? Before I take Ebube Chukwu.
Yes, sir. Thank you, sir.
You're welcome. So Ebube, go ahead, please. Let's get your reaction. I can see your hand up.
Yes, sir. My question is this: the arrows. Sorry, can you hear me, sir?
I can hear you now.
Okay. Yeah, my question is this: the arrows you drew concerning the outputs occurring before input transmission, which one of them is it? Is it the one to the left or the one to the right?
The output occurring before the input?
Transmission, yes, sir.
So that's to the left, right? When the signal...
Okay, sir.
Yeah, well, we'll get to that. We are still going to come to that today. It's a very interesting, it's one interesting aspect we'll talk about, okay? So that you see, when you begin to do signal processing, that you want to process your images, you want to find, we have a lot of computing systems, you want to do computer vision, you just play with your data files, then you do your extraction and all of that, you play with some codes. You really do not get to see the feel of the statistical process. the underlying statistical process in all of those things. You are just playing with codes and you are just getting results, okay? But from this perspective, you begin to appreciate what's going on there in your machine learning, in your whatsoever it is. Okay, Adelusi, go ahead, please.
Morning, sir.
Yeah, good morning.
Have you got us, sir?
For the ones that
Yeah, good afternoon.
Yes, sir. So,
like a lot of
yes, sir.
parts of the application.
I just wanted to ask if at every point in time that the graph would be straight, like can it have curves, and then even if it does, is it still possible to find the reverse time graph?
I don't understand. Probably a curved graph like this.
Uh,
Yeah.
like as it has curve, is it also yes, sir? If
You mean
it has curve,
something like this?
let's say from left to right.
Okay,
Yes, sir. Let's say
something
something like
like
that.
this.
But it has yes.
Yeah, sure.
So is it still possible?
Why not? Why not? It's still possible. This is just digital. Don't forget we also have the analog, right? So whatsoever we can do in the digital plane, we can do in the analog plane. But be rest assured that we have two domains, okay? Only that for us to be able to interpret our signals in the real world, we have to go analog. But if we now have to come to the computing system, so we have to digitize, okay? Because what the computer understands is some zeros and ones. So we have to find a way to digitize. That's where we now do our quantization, we do our sampling and all of those things, and then come to our zeros and ones. Then for us to be able to appreciate it again, then we have to come to the analog plane. But regardless of all of this, the same principles apply. Is that okay? Adelusi, is that clear?
Yes, sir. Yes, sir. Thank you, sir.
Yeah. So the reason I'm using some of these digital simplified images is just to make it easy to understand. So the idea is you understanding the process. So once you understand how it works, then you should be able to deal with the complexities. Okay. Now, how about odd signals? So if we should perform time reversal for an odd signal, we have that it will be the same as negative S of t. Sorry, this should be S of minus t, right? Yeah, time reversal should be equal to negative, just the same as sine minus t is the same as minus sine t. Okay. So if we perform same in the digital plane, oh, why do I keep forgetting my negative? Okay, negative n will be the same as minus s of n. Okay. So we know that our sine of negative theta is the same as our odd signal. Sine of sine t is odd. It's an odd signal. Okay. Now, the idea about the odd signal is that it is actually anti-symmetric. Remember, we mentioned that the even signal is symmetric about the signal axis or the y-axis. So the odd signal is anti-symmetric about that axis, such that the odd signal must go through the origin, okay? So if we have a signal, say like this, then this is an odd signal, okay? S of t, and then we have t, because the odd signal must go through the origin, okay? Must go through the origin. And by the time we perform, say, time reversal on, say, this signal, so this is, let's say, 1, And let's say this is also 1, right? So this is 0. So on the time axis, so 1 times 1, so it's going to give us -1, okay? And which is going to come this way, okay? Because everything switches, including the amplitude, okay? Take note of this. So we perform time reversal, but at the end of the day, the negative sign multiplies both the amplitude and the entire signal, okay? So the signal itself reverses. So this is -1, okay? Okay. Now, we'll move on to conjugate symmetric signals, okay? Go ahead, please. Opera Wilson. Go ahead.
Okay, good afternoon, sir. Sorry, for when you were doing the for the odd signals, sorry, for the even signals, you said that the multiplication did not affect the amplitude. It was just the time. Yes. But now when you're doing when you were like doing it for the odd signals, how come the multiplication by negative is now affecting?
Interesting.
Yes.
Now, so it's like
why is it not just changing the position of the time? Why
exactly.
is it changing the position of the amplitude?
Interesting. So it's like we performed a little magic, right? Now, okay, this is it. So let's come back to it. So we said our cos theta is even, right? And should we come up with cos minus theta is the same as cos theta, right? Now, when we deal with our odd signal, which is sine theta, this is the same thing as, now, if sine minus theta will be the same as minus sine theta. Is that clear?
Yes.
Now, you now see that for the odd signal, the negative that impacts on the time, in our case, theta is time, all right? So I know you are used to theta in your mathematics, right? So we're not trying to tell you, well, all of those things you've been playing with in mathematics, your trigonometry and all, they were actually talking about signals. So all of those mathematical ideals or ideas applies. So we're going to be coming back to them, okay? Now, the idea is this: for the odd signal, sine of minus t or theta is the same as minus sine t or theta. Okay, and once you punch that in your calculator, you see we are saying the same. Now, in other words, the time reversal for your odd signal impacts on the entire signal. So this sine theta is more like saying, well, our amplitude in this is -1 dot sine theta, right? Because 1 being the amplitude here seems not to be represented. And you now see that this negative is literally causing a shift of the entire signal. Okay? But in this case, the negative does not impact the entire signal, but it impacts only on the time for the even signal. Does that make sense, please?
Yes, it does.
Okay.
Yes, sir.
Okay. Yeah, so we now move on to conjugate symmetric signals. I remember when you played with your complex numbers, you talked about rationalizing. When you want to rationalize, you change the sign of the sign of the imaginary component, isn't it? You used to remember that?
Yes, sir. Yes, sir.
See, 2 plus J3. You want to rationalize, you say, okay, 2 minus J3, right?
Yes, sir.
So what we're actually doing here is conjugate, right? We call it conjugate.
Yes, sir.
When the sign of the imaginary component changes, then it becomes a conjugate component. Yeah, so that's what we are coming back to do again. So what I'm just trying to make you understand is that, well, I know some of you must have wondered, why are we doing all of this mathematics? Why are we doing all of these? They seem not to relate. Well, now you see how they relate, okay? They were actually preparing you for your signals and systems and every other thing you get it. Okay, Ibukun, go ahead, please.
Good afternoon, sir. Yeah, you said the sign of the imaginary part changes. Is it only the imaginary part or the real part can also change sign to find the conjugate?
What do you mean now? I didn't get your question, please.
Sorry, can you hear me?
I can hear you very well.
Okay, yeah. So you said in your explanation of the conjugate, you said that the imaginary part is the one that changes sign. And my question is, can the real part also change sign while the imaginary part retains its sign, and then the resulting equation is also still a conjugate?
Okay, now we'll come to that now, because we're also going to talk about the anti-symmetric signal, okay? Because for the anti-symmetric signal, we are going to have a negative of the conjugate symmetric signal, okay? So we are coming to that. So there we'll be talking about the anti-symmetric, okay? So we are going to see the two parts to this, the conjugate and the and the conjugate anti-symmetric signal. So we'll not see that. But when we talk about complex conjugate, in mathematics, it is the imaginary sign that changes. So the sign of the imaginary component, when the sign of the imaginary component changes, we say we have a complex conjugate of that signal, okay? But in our case, we try to place an asterisk on the signal. So if I say S of t is my main signal, then I want to say, well, S star of t is my conjugate, is the conjugate of that signal. So it means that if this, for instance, I'm going to come to you, Julius, just a minute. Now, if this is S of t plus j, say this S1 of t plus j S2 of t, then it means this is going to be j1 of t minus j S2 of t. Okay, but what if the time the time scale of my real or even signal changes? Now it will not impact on the signal because it's an even signal. Okay, so what if both are odd signals? Then the sign will still change and we'll come to the same thing. But don't worry, we'll get to that. So Julius, tell me.
Sorry, sir. Sir, can you go over that even signal again? I get the odd signal, but sir, can you go over that even signals again?
Okay, even signals. As far back as when we were talking about even signals, or in relation to conjugate symmetric, I want to know how far I need to go.
No, sir, just pure even signals, sir.
Okay, just even signals. Okay, so we'll take the even signals again. Okay. Now, for the even signal, what we said is that just recall your cos t, okay, is the same as cos minus t, right? So it means that if I should take the cos of a negative value. It's more like it takes the modulus of it and still gives me my positive value. Okay? And so
Okay, sir.
now if we now have a signal, for instance, this is very simple, a very simple signal. Should we perform time reversal? What we are doing here is time reversal on this signal. We are saying that it should be the same as the original signal. But if it is not the same, then it means that it is not an even signal. So now, to clear all that, let us use different colors for both sides. So this is -1. This is +1, right? This is t. This is s of t. So now we want to perform time reversal on this signal, right? So that this will now be s of -t. Are you with me, Julius?
Yes, sir. Yes, sir.
So now, if we perform time reversal, then it means that we are going to multiply the time scale by a negative value. Okay, so this is +1, this is -1, right? So we also have +1 here. And then going by our axis, we have -1 here. So this is 0, this is 0. So if we multiply this 1 by -1, so that would be negative times -1, right? That's going to give us +1, right? Are you with me?
Sir.
So it means that
Yes, sir.
particular axis, if we now have to plot it on this axis, we are going to plot it on +1, right? And the amplitude, nothing changes on the amplitude because the negative sign does not affect the entire signal. So we retain our amplitude. So it comes this way, right?
Yes, sir.
Now, let us now attend to the other part. So +1 times negative is going to give us -1. So it means that this now is going to be plotted as -1, right? And the amplitude is the same. So you see that there's a flip, okay? So this signal is more like flipping about the s of t axis, which you call the y-x axis, right? So the y-axis. So you now see that this part just moved to this part, while this part just moved to this part. There's a flip, but the signal is still the same. Nothing is changing. Now, if I didn't use different color, you wouldn't even know I performed any operation on this signal.
Yes, sir.
So it means that s of t is the same as s of -t. So let's call this so that you see the minus clearly. Okay. Is the same as s of -t. So since this is true, it means that when we have a signal and we perform time reversal on the signal, and the time reverse signal is the same as the original signal, we now say it is an even signal.
Okay, sir.
Which is consistent with what you already know in your mathematics, right? So Adeni, go ahead, please.
Yes, sir. So, you said when you perform the time reverse on the signal, that the x of t becomes x of -t, right?
No, s of -t is the time reversal of s of t.
Of x of t, yes, sir.
This is
time
reversal.
Yes, sir.
Of.
So, sir.
Go ahead.
Yes, sir. So why is it that the what do you call it again? The x of t did not go down? Reason because yes.
Why did
the x
not go
the
down?
time reversal? Why did it not go down the graph?
I don't understand. Why did this amplitude not come down?
Yes. Why didn't it come down on the graph?
Yeah. Why didn't this amplitude come down? Because we did not perform amplitude reversal. That's another operation. So when we perform amplitude reversal, we'll be doing something else. Then, because if we multiply the amplitude by a negative value, it will flip about it will fold about the time axis. But that has nothing to do with the meaning of the even signal. So what we are trying to address here is, what does the even signal imply? So we are working with the definition of the even signal. Okay. And now we're already liking the even signal to what you already know in your mathematics. Although they did not mention that it was a signal, we're not saying that.
Yeah, I tried using the space field, but it did not just
And when we perform this operation, well, Adelusi, you may want to mute your mic so that we don't get disturbed with the background noise. Okay, so long you can hear us. Now, so when we perform time reversal on a signal, and then we get the same signal as our output, then it means that it is an even signal. So a typical example is your cos theta. So you can try it. Try cos minus certain value. You see it's going to give you a positive value. But when you try cos sine of that same value, it's going to give you a negative value. So it means that the sine component is an odd component because the operation on the time impacts on the entire signal. Why for an even signal, the operation on the time does not impact on the entire signal. So soon you will realize, or you get to know why we usually attempt to suppress the odd component of our signals, although it carries the same information the even signal carries. It's more like a duplication of the same content. Okay, when we come into signal processing, you now say that, well, the information we're trying to pass across with the even component is also contained in the odd component, only that there is a flip in its positioning. Okay, so we don't want to start dealing with that because of the orientation. So that's where you talk about the suppression of a certain sideband in your modulation activities as you begin to go into applications and all of that. Okay. But we just wanted to understand, okay, how these signals interact. Is that okay, please, Adelusi? Are we good?
Yes, sir. Yes, sir. But sir, let me just ask for you. You said that because this is not the amplitude reversal signal, that we're not flipping the amplitude, right?
Yeah, this does not call for the flipping of the amplitude. But the odd signal demands that the amplitude flips. Because
yes, sir, thank you.
Sine minus t gives us minus sine t. Is that okay, Adelusi?
Yes, sir. Yes, sir.
But the fact that now there's a caveat here. Okay, there's a caveat. The fact that the amplitude flips does not necessarily make it an odd signal. If that signal does not go through the origin, it is not an odd signal. So in other words, if I should perform amplitude reversal here, and then the signal now comes this way, it is still not an odd signal because an odd signal must go through the origin. Is that clear?
Yes, sir. Thank you, sir.
Okay.
Yes, sir. Clear.
Yeah, okay, Abib, can we hear from you? Your hands have been up for a long time now.
Okay, thank you, sir. I wanted to ask for a confirmation about
what now?
the definition of conjugate symmetric signal. My network was breaking when you're conjugate symmetric signal and conjugate complex.
Conjugate symmetric and conjugate complex, or complex conjugate?
I'm not really sure. My network was breaking, so I didn't quite hear you well.
Okay, yeah, just before, yeah, don't worry, I'm going to go over it now. I was about to do that before the questions, just came right in. So we'll get to that right now, okay? So we'll just take it all over again. So the conjugate symmetric signal. Now, for the conjugate symmetric signal, there's something I want you to take note of, because we already made mention of the complex conjugate. You already know what the complex conjugate is, okay? So from your mathematics, your complex conjugate simply means change of the sign of the imaginary component, right? So when we have, say, S1 of t plus S2 of t, oh, sorry, not to the power of that, S2 of t, say is equal to S of t, then the complex conjugate will be a change of the sign of the imaginary component, which is S2 of t. So it means this positive is going to turn negative, so that S conjugate t will now be the same as S1 of t minus J S2 of t. That's the implication, okay? That's what it implies, okay? Now, if that is clear, then what is conjugate symmetric signal? So we already know what it means when we say conjugate. Sorry, I didn't spell that correctly. That's conjugate, right? Good, better. So we already know what conjugate means. So when we see the word conjugate, then we know, well, the sign of the imaginary component is going to change, but we are not talking about symmetry, okay? So when we talk about symmetry, then what we are trying to say is this, that the signal S of t is going to be the same as the conjugate of the time reverse signal. So when we have this, then we say we have a conjugate symmetric signal. So it means that the original signal, this is the original signal, is the same as the complex conjugate. This is the complex conjugate of the time reverse, signal, or of the time reverse version of the original signal. So we have the original signal, which is now equal to, now we already know when we have this asterisk added to it is a conjugate. So it's now the same as the complex conjugate of the time reversed signal. So it means that when we have a signal, say S of t, so let's change the color so we could emphasize that point. So it means that when we have S of t to be the same as S1 of t plus J S2 of t, so we now want to perform the time reversal, okay? If we perform the time reversal, for instance, so that will be S of minus t. This would be the same as x1 of minus t, right? Plus JS2 of minus t, right? Then once we do this, we will now perform the complex conjugate of this time reverse signal, which will now give us S1 of minus t. The sign now changes from positive to negative J S2 of minus t. So that if S1, if this is even, let's change the color. If this is even and this component is odd, then what we are trying to say is that S of t, which is the same as S conjugate of minus t, will be the same. Now, this, since it's even, it means that S1 of minus t will be the same as S1 of t. So we are now saying minus into bracket. Now, minus j into bracket. Now, S2 of minus t, if it is odd, will now be minus S2 of t, right? So technically, this will now be the same as S1 of t minus times minus plus j S2 of t. So it means that the original signal, which is this, is the same as this. Hence, this is conjugate symmetric signal. Go ahead, please, Abdul Malik.
Sir, please, why does that x1 of minus t, how does it become an even signal? What makes it qualify as an even signal? And js2 of minus t, what makes it qualify as an odd signal?
Okay, now we already played with your complex signals, right? If you remember.
Yes, sir.
So let me wipe this part so that we just recall our complex signals. We already played with complex signals, and we said that complex signals, the complex signal is the same as the sum of the even signal and the odd signal, right? And we already know that,
yes,
that the even signal is the same as the sine t, for instance, while the odd signal is this, no, sorry, cos, is cos, right? Cos t is the same as cos t. The even signal is the same as cos t, plus while the odd signal is the same as sine t, which is your complex. This is a complex signal. Now, from your mathematics, this is what you know as a complex signal, isn't it?
Yes, sir.
Yeah. And we are saying that this is the same as the sum of even and odd component. And we already know that this is also the same as cos minus t minus j sine minus t, right? Because if we perform the time reversal, then the negative comes out, right? So that what we are dealing with here is the same. So we have the imaginary part here. So we already know that our imaginary part is odd signal, and our real part is even signal. So that's what informed this process. So we only perform time reversal and then perform the conjugate, but that did not change our even signal from being even, neither did it change our odd signal from being odd. But by way of extension, we've been able to see that the time reversal of the conjugate signal is the same as the original signal. And when that happens, we say the signal is conjugate symmetric. Is that clear, please?
Yes, sir.
Okay. Now, if that is true and if it's clear, then why should we bother about all of these conjugate symmetric or anti-conjugate symmetric signals? But well, I just want you to take note of this, that oftentimes we want to be able to identify revalued signals, okay? When we talk about conjugate symmetry. And this is very useful when we begin to do a fast Fourier transformation, which we use in digital signal processing, okay? We do inverse fast Fourier transformation when we talk about OFDM and all of that. So if you look up some of my publications, you see, okay, well, I've done a little work in that regard in terms of proposing some modulation techniques for optical communication, wireless optical communication, okay? Now, also for filter design, okay? So this conjugate symmetric activity is very, very, very helpful and useful when we begin to do spectral analysis, okay? Because we actually want to analyze that signal. And just like I mentioned earlier, the information we want to transmit is contained in this even component, and the same signal is contained in this in the odd component. Okay, and you see that when you plot, you know, when you make your plot, you see that we are moving all the way, right? All the way from your imaginary to your real axis, and then you do your plot and all of that. So you now say that even though we clip off one part of the imaginary axis and retain one part of the real axis, then we still don't have any problem. We still have that same signal. We have the information, okay? So, and then when we now decide to do spectral analysis, we want to concentrate on analyzing just 1/2 of the spectrum. So either the positive frequencies or the negative frequencies. So what we're trying to say is that the information that is contained in this part is the same information that is contained in this part. So if we clip off this part and remove it, we have not lost the information. But when we do this in signal processing, we are maximizing the bandwidth, because we need twice as large bandwidth to transmit the whole of this. Just half of the bandwidth we transmit this. So if we get rid of this component, for instance, say it's the imaginary part, then we transmit just the real part. We are able to conserve our bandwidth. So we just use limited bandwidth to transmit the information we would have transmitted for transmitting the entire complex signal. Okay, so now this conjugate symmetry helps, you know, in signal analysis, when we talk about signal decomposition, even in filter design, you know, and so many other interesting applications, okay? So I wanted to have that just at the back of your mind. I don't know why we keep saying back of the mind. I think I'll prefer it's in front of your mind, okay, so that you always remember it and don't forget it. Okay, so can we move on? Can we progress?
Yes, sir.
Okay, so now let us look at the conjugate anti-symmetric. Conjugate anti-symmetric signal. Okay. Now, for the conjugate anti-symmetric signal, what we are trying to do here is that we not only perform time reversal, we're also going to perform what we call amplitude reversal, okay? So once we perform all of those operations and we are able to come up with the same signal, then I think we are good to go, okay? We now say, well, that is what we have. So technically, for the conjugate anti-symmetric signal, so S of t will be the same as the amplitude reversal, reversed component of the conjugate signal after performing the time reversal, okay? So this now is the same. So it means that the original signal is the same as the complex conjugate of the time and amplitude reverse signal. Okay, so it means that if, for instance, we have say S of t is the same as S1 of t plus S2 of t. So the first thing we want to do is to perform time reversal. So that'll be x1 of minus t will be the same as S1 of minus t plus, so this is j, sorry, j S2 of minus t, right? So we have performed time reversal here. Then afterwards, we now perform the conjugate symmetry of this. So that will be X. What am I doing now? So this is not S1 here. This is not S1. That's S of T, yeah. That's S, yeah, this X. So the conjugate of this, of the time reverse signal, will give us S1 of minus T. So it'll be minus, that's the conjugate, JS2 of minus T. Then we now perform the amplitude reversal, minus S conjugate minus T will now give us minus X1 minus T. Minus times minus become plus JS2 of minus T. So here we have performed amplitude reversal. So once we perform all of these operations, so we are taking the complex conjugate of the signal, then we perform time and amplitude reversal. Now, if we get this to be equal to this, then we say that the signal is conjugate symmetric. But now I'm going to mention some interesting practical sides to this, because conventionally, though we've not gotten to transforms, but it would be good, you know, that the, let's just place it here, that, okay, that the conjugate symmetric signal, despite the definition we already gave, for us to be able to have this, say S of T, okay, for a signal S of T to be conjugate symmetric, then it means that its Fourier transform must be real valued time domain signal. Okay, so just like I mentioned earlier, so with this, we are able to neglect or suppress or figure out a way to eliminate the imaginary component, okay? Because the information we really need is is also in the revalued signal, okay? And then the for a signal, when we talk about the conjugate anti-symmetric signal. So the signal S of T will be conjugate anti-symmetric if its Fourier transform is imaginary, purely imaginary, okay? Okay. So when we take the Fourier transform of the signal and then it is revalued, it is conjugate symmetric. Now, when we take the Fourier transform of the signal and it is purely imaginary, then it is conjugate antisymmetric. Now, this will be very, 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 very useful when we begin to play with signal processing, okay? Because when we get to transforms, that's where we really come into the implementation of the signal and systems ideals or ideology, okay? We want to process the signals. That's our goal, okay? So what do we really need when we want to process the signals? So then we begin to deal with that, okay? So when we want to analyze the signal construct, then we now figure out, okay, fine, what's of interest to us? Is it the imaginary or the real component? So if I should move from the ROF plane, then I have to figure out a way to eliminate the imaginary component completely. Because one, I have two things to deal with. Now, your regular signal, it is complex value, right? So this is what we play with in RF. But if I should go to my optical, okay, so I want revalued. So I don't want complex signals in the first place. Okay, so, and I also need it to be unipolar, okay, rather than complex. Okay, revalued unipolar, not complex, bipolar. Now, this is complex and it is bipolar, okay, because I have my positive, negative side and all of that. But for my optical, I want to eliminate the imaginary part because I need revalue signal, so my conjugate symmetry becomes handy, okay, because when I take my Fourier transform, I want to take that into consideration. Then I want to make sure my signal is also unipolar. So I want to figure out a way to eliminate the imaginary component. So a couple of things comes into mind depending on the plane you are trying to analyze your signal, okay? So oftentimes in the radio frequency domain, like you do in your mobile communication, your broadcast and all of that, you are literally playing with bipolar complex signals, okay? So if you now switch to the optical, wireless optical and all of that, you now want to begin to deal with unipolar revalued signals in terms of application, okay? So, well, there's nothing to worry about yet. We are just trying to play with the basics and the fundamentals, okay? So, okay, then what else? What next? Okay, we have periodic and a periodic signal. Okay. Okay. Let us come to this. Any question, please? So I know if we could progress. We still have a few minutes. Oh my goodness. We are really running behind time. I thought we'll be able to cover so much. Okay. Now, I already made mention of amplitude reversal, so we don't have to. So we have your periodic and a periodic signal. So when the signal is not periodic, okay? So when we consider a continuous time signal, say S of t, we'll say that it is periodic if it is defined over the fundamental or the time period, cap t, for all values of t, okay? Such that the fundamental time period t naught, which is not the same as t, is the smallest value of t, okay? For which the signal is periodic. So t naught is the smallest value of t for which the signal S of t is periodic. And then t naught will be the same as the inverse of the fundamental frequency. So where F naught is the fundamental frequency. Okay, Ibukun, tell us. I can see your hand up.
Okay, good afternoon, sir. So I think I just want to sort of clarify the previous slide you did. There were lots of concepts and terms you sort of threw around, but I want to believe that was just a sort of digression. You were just trying to point us to things that you still teach in the future, right?
Trust me, I did not get what you just said. Please try to explain again.
Okay. Okay, sorry about that.
Okay.
So I said in the previous slide, the one
Okay.
before you started explaining periodic and aperiodic signals.
Mhm.
You talked of conjugate symmetric and conjugate asymmetric signals. Then you branched into Fourier transforms and we started talking about bandwidth and
Okay, the application,
part of that. So
the application,
yes,
yeah, of
yes,
conjugate and anti-conjugate symmetric. Okay, yeah.
yes, with the Fourier transforms and also I just want to clarify because I think some people got confused that was you explaining everything. So I believe that was just a sort of digression to things that you still teach us later?
Is it really digression? Well, we are still going to teach or talk about Fourier transforms, Laplace transform, Fourier transforms, Z transforms as separate topics, okay? But the applications, well, that wasn't digression. That was more like an addition. Probably we didn't mention some of those in our previous video. So just add that as an update to what you already have in the previous video, okay? So at some point you want to know how these things apply. We just mentioned them, but beyond mentioning, we should be able to tell the applications. Yeah, that's it. Yeah. Okay. Thank you.
Okay. Okay. Yeah. So are we expected to understand those applications right now? Like what they mean right now?
Yeah. It will also enhance your learning. You just need to, you want to know why you do what you do, right? I think that's a way of spicing up the game. And so you don't want to tell me, well, you're in the university because mommy and daddy wants you. You're in the university because you want something, right?
Yeah. And the only issue I just think is that a lot of us probably don't understand the terms you were using, so it might not make a lot of sense.
Don't worry. There's nothing to worry about right now. As we progress in the system, you in this course, you'll become comfortable with all of those concepts. Don't worry. Okay, don't worry. And I'm sure you have access to the video, so you could play back and then use that as a basis for your revision. Okay. And should you have any questions, then you could ask in the next class. Don't worry if you're unable to ask right now. Is that okay?
Yes, it is. Thank you, sir.
Okay, so we have Olaoluwa. So tell us.
Yeah, good afternoon, sir.
Yeah, very good. Yeah, we've got so much greetings today, so just go on.
Okay, so when I was looking at the definition of periodic signals, and the fact that we have T naught there, does it mean that we can have like multiple values of the period in a single signal? That's what I want to confirm.
Okay. So I will take that. So I think we got another hand up. So can we take all the hands? So the next guy. So tell us.
Sir, I don't wanted to ask if you can drop the recording of the class after the class because the network is not good here.
Okay. Definitely, I'll do that. I'll do that.
Okay.
That's not a problem. That's not a problem.
Okay, sir. Thank you, sir.
Okay. Now, our good friend just asked, well, now looking at this definition, we just said the periodic signal is a continuous time signal, S of t, said to have this period value or time period value, okay, said to be periodic with this time period t. If there's a positive non-zero value of that value t defined by this, and we are saying, well, t naught is the smallest value of t. So it means there are multiple values of t. If t naught, which is the fundamental time period, is the smallest value. Does that answer your question?
Yes, but there's a bit of a follow-up too. Because T is like periodic, so like because the fact that we have like a periodic signal means that the signal probably repeats itself. So if we have multiple values of the period, does that mean that we could still have like maybe the function doesn't like repeat itself because we have different like values of the period?
Okay.
So I hope you understand the question.
I understand your concern, but this will become even more interesting when we talk about harmonic signals, okay? Where we have signals repeating at a certain value of the fundamental time period. So when we get to Fourier series and all of that, we are going to come into this, okay? So that when we do featuring, what are we trying to do? We are trying to eliminate some other frequency component of that signal. But mind you, we now have F naught, we have N F naught, where N will take on values from 1, 2, 3, all the way. So when N is 1, so we have the fundamental frequency component, right? So we can have 2F naught, 3F naught, 4F naught, all the way. So these are integral multiples of the fundamental frequency. And we know that this fundamental frequency is the inverse of the time period, right? So F naught is the same as 1 over T naught, right? So it means that these are integral multiples. Is that clear? So you don't worry. So when we begin to talk about harmonics, harmonic signals and all of that, so a lot of signals really that we could, play with. Yeah, even moderate signals in digital processing and all of that. So what we want you to pick right now is that we did not define the periodic signal with respect to the fundamental time period, because that fundamental time period is the smallest value of the period for which this signal can be periodic, okay? So technically, other values of this time period exist in the signal, okay? So, when we talk about practical signals, you have to take your mind off your clean sinusoids, okay? Because we have signals really messed up, all the way, something like this. So at the end of the day, when we do the analysis, you now see that, well, these are integral multiples of a certain, so by the time we're able to get the smallest frequency value or the smallest, or let's say we're able to get largest frequency value, or better say the smallest time period, then we can now begin to do our analysis. So with that, you're not taking us to spectral analysis. Is that clear?
Yes, sir. Thank you, sir.
Okay, you're welcome. So the same applies for the digital. So if we talk about the discrete, so S of n is the same as S of n plus n, where this is the smallest positive integer that denotes the time period. So F naught in the digital plane will be the same as 1 over n. So it's just about that. So when we talk about a periodic signal, we're trying to say, well, these are signals or sequences which are not periodic, okay? And they also have their various applications, okay? We use them in signal processing, even in control and all of that, okay? So we'll talk about radar system, even your audio and speech processing, there where we begin to talk about aperiodic signals. For those of you in biomedicals and all of that, imaging, this seismology. So what we deal with there, they are all aperiodic signals, okay? So, well, you want to also look into that to see, well, what are the applications of this periodic and aperiodic signals, okay? Then we also have energy signals, power signals, and neither energy nor power signals, okay? So, okay, so I'll quickly run through those ones and then see if we'll still be able to do one or two things today, right? Okay, so unfortunately, we're unable to go to MATLAB. We started with that. So let's clear this. So we have energy signals. Okay. So when we talk about energy signals, what we're trying to say is that, well, a signal can be said to be an energy signal if its total energy value is finite. That sounds really basic. So it means that the energy value takes on value at some point less than infinity. And then the average power must be 0 when the energy value is finite. Okay? So we'll come back to Fourier transform again. Though, don't worry, we'll continue to mention it and then go back and forth till we now begin to talk about the transform itself. So we now say that the energy signal must be absolutely integrable. So it means that if S of t is a signal, for it to be an energy signal, it means that if we take the integral of the modulus of the signal, dt, it must be less than infinity. So it must take on finite value. Okay, Ihuoma, go ahead, please.
I wanted to ask that when you say like the energy value is finite, do you also mean like it's a defined value, like it's a known value, something like that?
No, no, we don't have to necessarily know the value. We're just saying that it cannot be infinite. It must take on a finite value. So some value less than infinity. Okay. So we cannot really say we know the value. The value could be 1, it could be 2, it could be 100, it could be 15, but it cannot be infinity. Okay. And if that is that, then the average power of that same signal must be 0. Now, if the average power of the signal is not the same as 0, we cannot say it is an energy signal. Okay. And just before I come to Lawal, some other properties which you have to look into to ascertain that it is an energy signal is to take the integral of the modulus of the signal, which I just did here, okay? So once you do that, and it's also a finite value, then it means that it will have a Fourier transform, okay? So if meaning this S of t must be, it means that S of t is absolutely integrable, okay? For the integral of the modulus value to be finite. And if it is absolutely integrable, then it means that energy signals must have Fourier transform. So it means that it's not all signals that can have Fourier transform. Did you take note of what I just said? I just paused for a reason. And I said, not all signals can have Fourier transform. Did you catch that?
Yes, sir.
Yes, sir.
Yes, sir.
But energy signals must have Fourier transform. Okay? And then the total energy is the same as the area under the graph. So it means that for us to do that, the integral of the modulus squared, the t, is the same as the energy value when we take on values from negative infinity to positive infinity. That's why most of the time, I'll come to you guys shortly. That's why most of the time, when they talk about energy value, they talk in terms of the square. Okay? Now, in your fundamentals of electrical engineering, how do you express your energy? Hello? How do you express your energy?
Energy equals to IVT.
Yeah.
Okay, with respect to time.
I
right?
square RT. I square RT.
So, but the bottom line is I squared, right? Or V
1/2 K equal.
Yeah, so when we rationalize the resistor, so we can say the approximate value of your energy is I squared or V squared, right? So you now see that the square of the value of my signal is actually the energy. That's where we got it from, okay? So that the average power P, we now take on the limit of E over T, which is equal to 0. So it means the power of the signal, let me change the color. It means the power of the signal is 1 over T, integral 0 to T, mod S of T squared dt. Okay? Now, if this describes my energy signal, so let us come this way. If my energy signal is such that the value of the energy must be finite, such that the power is equal to 0, how about my power signal? So my signal is said to be a power signal if and only if the average power is finite, okay? So it means that the value of power must be finite, but the energy must be infinite. So periodic signals are power signals. And power signals may not necessarily be periodic signals, okay? And then one other signal I want to talk about is signals that are neither energy nor power signals, okay? So they are neither this, okay? So they do not meet with this property, and they also do not meet with this property. So we call them neither energy nor power signals. Okay, now let me take the questions that those that have been raising their hands. So can we hear from you now?
Yes, good afternoon, sir. I wanted to know, you said the energy signals must be absolutely integrable and they have Fourier transforms. Does it mean signals that have Fourier transforms, that is, signals that are absolutely integrable have Fourier transforms?
Yes. So when we get to Fourier transform and Fourier series, we are going to talk about the Dirichlet conditions. And one of the Dirichlet conditions is that the signal must be absolutely integrable. Then they should have finite maximum and finite minima and all of that, you know. So we'll come to that. So there are conditions for signals to have Fourier series. There are conditions for signals to have Fourier transform. Okay, so then for that to happen, we must talk about the Dirichlet conditions. Okay. So we'll still get to that in your study. Don't worry.
Thank you, sir.
You're welcome. So tell me. Go ahead, please.
Yeah, I wanted to ask if we could, because of the formula for the energy signal, it showed that we have to find like the integral of the function over like all values of time, I think. So what happens if we have like a discrete signal? Can you still find the integral of it, or can discrete signals be energy signals? Because they won't always have a value for, like, I don't think that that defined for every value of time. It's only like fixed points. That's the question.
Okay. Now the fact that they have values at distinct intervals means that they actually have values over the spread of time. So I want you to get that clear. So this is the spread of time. So it takes some value here. It takes some value here. Take some value here. Take some value here. Take some value here. Take some value here. So for us to get to this point, we must have sampled a continuous signal. Okay? So you don't worry. Yeah. So at the end of the day, we must meet the energy or power signal or neither energy nor power signal conditions. Okay?
Okay, sir.
Mm-hmm. So, so the bottom line now is, okay, we want to play with examples and all of that, the applications, where can we apply them? Okay, so, you know, those are the things. So we're talking about energy signals, we have power signals. So, for the energy signals, digital communication, perfect. That's because we are playing with energy signals, because they should have Fourier transform. Else, we will not be able to perform a fast Fourier transform algorithm. We'll not be able to apply fast Fourier transform algorithm on them. So we target energy signals. So digital communication, yeah, when you do post modulation and all of those, okay? So because finite duration and finite energy signals, okay? Then when we talk about power signals, usually they have infinite duration, okay? So we use them as carrier signals. So you can use them in broadcasting when we do noise analysis, past spectral density and the likes, okay? But we target energy signals when we want to really perform some intelligible operations, okay? We want to transmit signals and all of that. Then when we talk about your neither energy, power signals, we have RAM, your RAM signals, okay? That just spike off, okay? Okay, so such that it has infinite energy, infinite power, okay? So you can use them in system response analysis control systems, okay? Now, another example of neither energy nor power signal, I just mentioned ramp, okay? You also have Dirac delta, do this, yeah. Okay, it's an impulse, okay? So just talk about impulse response, just one spike, an impulse. Okay, even your sinusoidal signals, okay, when you say S of t is equal to sine t, okay, because in a pure theoretical domain or dimension, it has infinite duration, okay. So we use them in Fourier analysis and modulation and all of that, which are even exponential signals, okay, because they're unbounded, you know, so we can use them for, you know, a whole lot of things. When you see all those economics activities, your stock market and all of that, they are doing financial modeling, population dynamics, so exponential signals, which are neither energy nor power signals, are very, very useful. Okay, so tell me, I thought we'll be able to go into signal manipulation today, but our time is, now we just have 3 minutes. So I think this would be a good place to stop. So before we say goodbye, so tell me, young man and Ariori, go ahead, please. You have the floor.
Okay, good afternoon, sir. My question is that when you were mentioning power signal, you said an example of power signal is periodic signals. While you were talking about NENP, you said sinusoidal signals. Now, and I want to ask, what is the difference between periodic and sinusoidal signals?
The difference between periodic and sinusoidal signals. Now, I said sin t, okay? So a sinusoidal signal goes beyond that, because we have to now define a periodic signal. We now have to define the frequency component, right? So it's not just sin t, it's sin t with respect to the phase value and the frequency component when we begin to talk about periodic signals. I don't know if that's clear.
So I don't get so.
Now, this is a sinusoid, right? But what if I specify the frequency, say t plus omega, let's say theta omega t. So this is the frequency component, 2 pi f. So which is the same as 2 pi t. So I've assigned a period and a frequency to this. So we can begin to talk in terms of periodic.
Okay, sir.
I don't know if that, you know, satisfies or meets your, but we are going to solve some problems to get things cleared up. Okay.
Okay, sir. It's clear.
Okay. So any other question, please? Any other question, Habib? Yeah, you can go ahead, please.
Okay, sir, when you were explaining energy signals, you said that all energy signals must be capable of undergoing Fourier transforms. What about power signals? Do they fall under the same condition?
Now, what you ask is, are power signals absolutely integrable? I just asked you a question.
No, I asked if power signals, do they all undergo Fourier transforms?
Then I asked you, are power signals absolutely integrable?
No,
Why?
because if we integrate them, then the energy output would be equal to infinity.
So then they cannot have Fourier transform.
Okay, thank you, sir.
You're welcome. So energy signals have Fourier transform, okay? So are we good to go? Okay, we are just in time. Hope the class was informative.
Yes, sir.
Okay, so we are a minute ahead of time and we can still see one hand up. So tell us so we could call it a day.
Sorry, sir. What does the term absolutely integrable mean?
Okay, I think I stated that earlier. So it means that if we say it is absolutely integrable, it means that if S of t is a signal, so if we take the integral of the modulus value of S of t with respect to t over the time interval, then it should be finite value. So it means that this value must be less than infinity for it to be absolutely integrable. This is what it means to be absolutely integrable. So it means once you have your signal defined, you take the integral of the modulus of that signal. If it gives you a finite value, then it is absolutely integrable. Is that clear?
Yes, sir.
Okay, so on this note, we'll say we'll meet in our next class. Hope you had a great time. So see you next week, God willing. Bye for now.
Thank you for the class, sir.
Wow.
Thank you, sir.
You are welcome.